sparse linear models or regression, and hopefully you have a good idea of what some of these high-dimensional techniques do. What I want to switch to is a discussion, like a detour, about these ideas of metric entropy and so related ideas. So this is more of an approximation, more of a math topic, but it's very useful in so expanding the toolbox and allows us to prove, let's say, bounds on random matrices. So that's what I want to do next. Control, you recall the operator norm, the norms of random matrices. So we want to talk about consistency of, let's say, covariance matrix estimation or estimating or controlling the norms of random matrices. So these ideas are useful there. They're also useful for analyzing non-parametric regression problems, where so linear regression, the function is linear, so you effectively estimate a low-dimensional parameter, right? So if you recall, we had something like this plus noise. But I can generalize this to a non-parametric regression model where so this, for example, could vary in, for us, it did vary in, let's say, L0 ball of radius S, let's say. They did work with this, or this could be in LQ ball, a radius, something like this, I believe. Something like that. And Q is in 0 to 1. But a more general model would be something like that, where f star belongs to some function class. So this, for example, could be the class of all functions that are one Lipschitz. So this is a much larger class. So this, so let's say one is a special case of 2, where you have f is a set of all functions that can be written as beta x linear functions, where beta is in some set. Let's call it like this, either S sparse or something like that. So linear regression, even a sparse linear regression, is a special case of non-parametric regression. So this is sometimes called non-parametric regression if you allow this function class to be something which is not finite dimensional. So the class of all one Lipschitz functions, this is an infinite dimensional class. It's much bigger than the class of all linear functions. Even if the domain is RD, this class is much bigger than this class. And one way to see it is through these ideas of metric entropy. So so these give you a measure of how big a set of objects is, set of functions is. Intuitively, you can imagine that this class is much bigger. This is includes a lot of nonlinear functions. But how do we measure how much bigger this class is relative to this? It's not clear. Okay, and how massive these classes are would determine how much how many samples you need to be able to estimate things accurately. Right, so if you have an infinite dimensional class like this, it's even it's counterintuitive that you can actually do anything here. So you have a sample size n. How can I estimate a function which has infinite degrees of freedom, infinite let's say infinite parameters basically. There's no parametric form that I can estimate there's not. So the things that we discussed so far gives you an idea that it's doable if you have some sort of a structure. So here, for example, beta would be in R to the D. D is much bigger than N. So the number of parameters is much bigger than the sample size. Still, you can do something if you have some sort of like a sparsity structure. This Lipschitz sort of property is a form of, it's like a structure. It's a form of smoothness constraint. This can, for example, be discontinuous, or it can vary. It can be like something like this. This is not one Lipschitz. It's like sine. It varies a lot, like fast, but something like this might be like one Lipschitz. So you can see, for example, you can show that the derivative of this in absolute value has to be bounded by 1. So if the derivative is changing a lot, so this rules out these things. So there's like a complexity constraint here, and we just want to quantify that. So you want to quantify that and then use that to somehow translate it into how many samples you need, or how fast your estimators converge as the sample size grows. Okay, so that's sort of the background of these ideas. So like maybe one Lipschitz. This is like maybe 100 Lipschitz. So Lipschitz with a constant of 100 maybe. So how many people have seen like metric entropy ideas? Covering numbers, packing numbers. Okay. Okay, good. You learned something today. So metric entropy ideas allow us to reduce basically considerations over massive or uncountable sets to finite sets. So it's a measure of, so metric entropy is a measure of the size of a set, and you can think of it as a quantitative measure of compactness. So anyone remembers what a compact set is from your analysis? Yeah. Yeah, okay.
Any open cover can be reduced to a finite.
Subcover, okay. This is a good definition. Are there other definitions? It's like closed and bounded, that's like a theorem. Like in RD, things can compact if they're closed and bounded. In a general metric space, they are compact if they're closed and totally bounded, not necessarily bounded. Any other definition? Every Cauchy sequence, that's the definition of compactness. So every like bounded sequence has a convergent subsequence. That's sort of compactness. Every bounded subsequence, or every bounded sequence has a convergent subsequence. So that's sequential definition. What Kyle mentioned is like a more abstract, the most general definition, which works even if if your topology is not defined by sequences. So T, let's say, is compact if every cover has a finite subcover. So what does this mean? So cover is like union of a bunch of open sets. So every open cover. So in particular, in a metric space, I can try to cover a set. I'm going to put balls of radius epsilon, let's say, around every point. Okay, so if you have a set, consider a point X with a ball of radius epsilon around it. Right, this covers some part of the set, and then I vary X with another ball here, and then another ball. So if you do it around every point, you definitely cover the set, right? So if I take the union over all possible X in T, definitely every X in T is in one of these balls, right? So this is, let's say this is the unit, like open ball, open ball of radius epsilon at X. So if T is compact, then there exists a like finite subcover. So I can find like X1 up to Xn subset T such that like there is some like I can cover by a finite subset of these. So T is going to be union over like I from 1 to n bxi epsilon. Okay. So if the set is compact, I can always find this. The metric entropy idea or covering number idea concerns with the smallest number n that can appear here. So what is the smallest number of balls that I can cover the set if I set the radius to be epsilon? And so you can imagine if I reduce the epsilon, then I need more balls, right? If I increase epsilon, I need less balls. So what is the smallest? So if you fix epsilon, what is the smallest number of balls or radius epsilon that, let's say, with centers inside the set that can, like, whose union is T, like contains T. It's a cover of T. This is equivalent to saying that for every x in T, there exists like I in 1 to n, such that I'm going to use the metric rho xi is less than or equal to epsilon. For every x in T, I can find one of the members in the cover, like the center of these balls, basically, such that the distance of x to xi is less than epsilon. That's equivalent to statement. So a set xi, I guess, sorry, like finite set, need not be a finite set, but any set, a subset of T with this property or equivalent this property is called an epsilon cover. So this is called an epsilon cover of the set, an epsilon cover, or an epsilon net of T. Okay, and the cardinality, the size of the smallest epsilon cover, is called the covering number. So this is these ideas with some change in the notation to match the book. So an epsilon cover or an epsilon net of set T respect to a metric rho is a subset of T such that for every T in T, there exists a theta I in the net such that the distance of theta and theta I is less than epsilon. And the epsilon covering number, so the function of epsilon and also depends on T and rho, is the cardinality of the smallest epsilon cover. The log of this quantity, the covering number, is called the metric entropy. So it's just a fancy name. As long as you know the covering number, you don't need to know the metric entropy like terminology, but it's just there in case you hear it. They measure the same quantity different ways. Okay, so that's the picture we have here. Oh, actually, this is another way of writing it, already mentioned. So in normal spaces usually, so this works in any metric space. In normal spaces, you usually have, the metric is the defined in terms of the norm, like that. And then you have the unit ball. And so these balls you can write as, so the ball of radius epsilon centered on theta j, they're basically shifted and scaled copies of the unit ball, right? So this is saying I rescale the unit ball to epsilon and I shift it to this position. So basically this is the set of all, this notation is the set of all points that look like this, theta j plus epsilon theta, where theta belongs to that's the kind of Minkowski's notation of writing sets. And so this set is an epsilon covering if T is like inside the union of these shifted and scaled balls. Okay. Questions? So here's a picture. So this is the set here. The T is like the bigger ball. This is, and then I'm covering it with smaller balls. And each one has a radius delta. So this is a delta cover. And you can see every point basically is covered. So every point is within, so I pick a point here, is within the delta radius of at least one of them. So it could be multiple, but So this point, for example, is within the delta radius of this one. This point is within the delta radius of both of these guys. So there's at least one point there. There's also like a complementary definition. Sometimes you don't need to put thetas inside the set. So if the set is in a bigger space, you might take thetas to the outside, but the balls like cover the set. That's called an exterior cover. And there's some simple relation between. So if you have exterior covering number, you can translate it to the usual cover. Just a side note, for us, usually we work with the thetas inside unless specified otherwise. There is a complementary definition, which is that of a packing. So a packing, an epsilon packing of a set is in a metric space is a set, let's say finite. It doesn't have to be finite, but usually it has to be finite. Set of points such that every pair of distinct point is within. So the distance is at least epsilon. So they're epsilon separated, sometimes called epsilon separated set. Epsilon separated set. So the cardinality here, it's hard. It gets harder as you add more points to the packing. So the cardinality of the maximum epsilon packing is something of interest. It's called epsilon packing number, and we use M to denote this. Okay, so the smallest cover and the largest packing, these are the quantities of interest. So here's a picture. Again, the points are inside the bigger set T, and you can see if I have a delta packing, if I put a ball of radius delta over 2, let's say, around every one of these points, these balls do not touch, because if they touch, it means that what would go wrong if they touch? So if it's delta packing, I put a ball of radius delta over 2. Yeah, so by triangle inequality, if they touch, there is a point whose distance from these two, let's say, is less than or equal to delta. Then by triangle inequality, the distance of these would be less than or equal to delta over 2 plus delta over 2 is less than delta. So it violates the delta packing. So a delta packing has this property that if I put a ball of radius delta over 2, they're not going to touch. Okay. You can see it's hard to put another point here. So you can try to put something here, but if I put a ball of radius delta over 2, I'm going to touch this. So this is already close to the maximal packing. Like there could be multiple maximal packings, but there's like one number. There could be multiple maximal packings, but there is either infinite, which usually is not the case, but if it's finite, there's a number, which is the cardinality of the maximum packing. So so here's a very simple example. Let's say for the covering numbers, if I have the unit ball, not the unit ball, yeah. Okay, so unit ball in R1. So the unit ball in R1 would be just the interval, -1 to 1. Okay, the set of all x such that norm x is less than or equal to 1, but norm is just the absolute value. So this is my unit interval, and then not the unit interval, just suppose I want to, this is my set P, let's say. I want to cover it in balls of radius epsilon. So how do we cover it in balls of radius epsilon? What is the smallest sort of? If I want to cover this set. What's the natural thing that you would do? Yeah, okay. Yeah, you start like, I want a bottle radius epsilon is basically something from minus epsilon to epsilon, right? So I have a set of size, like an interval of size 2 epsilon here to the center, and then the next one I pick here. So these are the sets that are going to cover, and the centers would be the epsilon net or epsilon cover. Right, and you can see this is sort of optimal, right? So if I have this cover, then they don't overlap, so I can do much better than this. So how many there are? Roughly this much. Okay, if you assume that this is an integer, then exactly this. If it's not, then let's say I add one more to it to make sure, like, account for the fractional issues. So that would be the covering number. An upper bound, and then you can probably show a lower bound. It's not much. You can't do much better than this. So it blows up as epsilon goes to 0. But what we care about is the rate at which it goes down to infinity. And the rate is 1 over epsilon. Okay. If you do this argument for the L infinity ball would be, this is actually all these balls, like all the LP balls in R1, but it would be like L infinity ball would be similar. It would be like in R2 would be like this, right? And I can discretize each one of these axes like that. And then you can see roughly I need 1 plus 1 over 2 epsilon to the 2 little sets here, right, to cover. And then in general, to cover the unit L infinity ball, which is this Q in RD in the L infinity ball itself. So in little like epsilon copies of the same thing, that requires this much. So this behaves like 1 over epsilon to the D as epsilon goes to 0. Okay, so that's how it scales, and you can see the dimension, so it's exponential in the dimension. This is an example, like a manifestation of the Kerasov dimensionality. So it blows up exponentially in D if you want to cover something which is in D dimensions compared to this, right? So this gets much, much worse than this if D is like 100. Okay, it quickly like gets out of hand. So a manifestation, something like that, of the Kerasov dimensionality. So sounds good. This behavior we can extend to basically covering any ball in a norm space in copies of itself. Okay, if I change this norm to, for example, L2 norm, it would be different. But as long as I'm covering the same unit ball in the same norm, the same idea, we'll see. Before seeing the more general result, any questions before we move on? So you get the like intuitive idea here, right? There is this lemma, which you can prove as an exercise. I'm going to hint at one of the points. So there is this relation, sandwich relation for packings and covering numbers. Okay, so we can also like do it in the other way. So packing numbers sandwich the covering number, and the covering numbers sandwich the packing numbers. You can just rewrite it m in terms of n. So there's not much loss up to constants that are sort of similar. So this inequality follows from this nice observation that any maximal packing is automatically a covering of a suitable radius. So any delta packing or any epsilon packing is basically automatically an epsilon cover. The reason becomes clear if you just think a little bit about it. So let's say delta. Here we have a delta packing. if this delta packing is maximal, it means that I can't add another point here that's separated from the other guys by a distance of at least delta. Then the claim is that then this set of points, exact set of points, is going to be a delta cover. Anyone maybe can think a little bit about it, give an argument, just a one-line argument. So we have a, let's say, n, assume is a delta cover, right? Then sorry, delta packing, maximal delta packing, then n is a delta covering. So why? I can add a point, right? So what would go wrong, let's say? If I can.
Radius delta any of the other centers.
Yeah.
Then you could add like that point to your maximal set. And then
Okay, great. So to we do by contradiction. Suppose n is not a delta covering, so there exists a point which is not in a ball of radius delta around any of the other points, right? So this is outside a ball of, if I put a ball of radius delta around every point, this is going to be outside everything, right? Also outside all of these balls. Then if I add this point to, this point would be basically, the distance of this from every point would be bigger than delta because it's outside the ball of radius delta. And so I can add it and I get a, like I'm going to contradict the maximality of the pack, right? I can grow the packing by one more point. So this suggests that the delta covering number is at most the maximal, like the packing number, right? Because this is the cardinality of the maximal packing, because that cardinality, for that cardinality, I have a delta cover. So the best delta cover has to have like less points. So this proves this inequality. The other one I'll let you prove. Okay. So these are useful because I can, for example, if I want to upper bound the covering number, I can upper bound the packing number, right? And vice versa, if I want to come like bound the lower bound the like the covering number, I can lower bound the packing number. But we're going to use this idea here, so you'll see how you're going to use that. So suppose now we have two norms on RD. So I'm using like prime to denote the other norm, and the respective balls are B and B prime. So this is the unit ball of this norm, and the other one, the prime, is defined similarly. So I put a prime there, right? B prime is the corresponding unit ball for the prime norm. Then we have this result, covering this unit ball of this norm in the prime norm satisfies these inequalities. So the covering number is controlled by the packing number, this we've seen, and the packing number is at most this. The covering number is at least that, okay? So this quantity is the volume. It's the d-dimensional volume, the Lebesgue measure, basically. And so to see why this is useful, consider the case where b is equal to b prime. So we're covering the ball, unit ball, in its own copies. Okay, epsilon scaled copies. Then this quantity, this is a Minkowski sum. This would be basically 2 over epsilon plus 1 times b. And this is a d-dimensional volume. The scalar comes out. So let me do it here. So we have volume 2 over epsilon b plus b is volume 2 over epsilon plus 1 times b. That would be 2 over epsilon plus 1 to the d volume b. So if you rescale set by factor alpha, then it comes out of the volume by alpha d. And so the right-hand side is volume 2 over epsilon b plus b divided by volume b. And you can see this is just 2 over epsilon plus 1 to the d. Okay, that's this bound. Upper bound and the covering number. If epsilon is less than 1, you usually care about epsilon small. This is bounded by 3 over epsilon to the d. It's useful to remember this. So if I, for example, do the L2 ball in L2 ball, then I need this many points to cover the L2 ball in the L2 norm. The lower bound is similar. So if you look at this, just the volumes cancel out, right? And so you get this. So you can see up to this constant here, this is a tight bound. So the covering number of the unit ball of a norm space in terms of its norm is roughly like some constant to the epsilon divided by epsilon to the d. So you can see similar to basically what we had here, right? So basically behaves like 1 over epsilon to the d. Okay? So let's try to prove this. So the proof, this is called the volume ratio argument, or basically compare the volume to sets. So first, we take an epsilon cover of b in the prime norm. So by definition, you have this inclusion, right? So b is covered by balls of radius epsilon centered at theta j's, which are just shifted version of the unit ball, rescaled unit ball. Then what? When we take the volume of both sides, this is less than or equal to the volume of this, right? Volume is a measure, but it's just like intuitively clear. Something is inside something else, the volume has to be less than or equal to that. This is bounded by this. Why is that? Subadditivity or union bound, basically, for general measures. Again, intuitively, it's clear. So if some union of a bunch of sets cover another set, the total sum of the volumes has to be bigger than the volume of the original set. Now, this is the Lebesgue measure. So Lebesgue measure is translation invariant. So the volume doesn't change if you move things around. So volume would be the same as this. And then this is going to be the same as epsilon to the d volume b prime, right? So prove that this is bounded by that. No, sorry, there's like an n. So each one is like that. So this is going to be bounded by n times epsilon d volume b prime. You divide both sides by this. So from this we get volume B divided by volume B prime. And then 1 over epsilon to the D is bigger than or equal to, less than or equal to n. So this is saying any cover has to be at least this much, right? So it gives you a lower bound, right? So how do we prove the upper bound? Proof of the upper bound. So you're going to use that inequality. I'm going to like control the maximal packing, right? So upper bound. Now let's say m theta 1 up to theta m is a maximal epsilon packing of B and B prime, right? What can we do here? If you have a look at this, so if I put a balls of radius delta over 2, right, they're not going to overlap, so they're disjoint. But the union is not contained in the original set. However, if I enlarge the set a little bit, right, so the worst case is that these are at the boundary. So if I just add to each point in the set one of these balls, right, so the set that's obtained, like as a Minkowski sum of this plus delta over 2 B prime, right? So this is the set whose elements are of the form x plus delta over 2y, where x is in B and y is in B prime. So this set would contain, this would be like something like this. Right, okay, you can imagine what this looks like. Right. Yeah. Just imagine the rest. Right. So this contains the union, right? So I would have basically union I from 1 to m, theta j plus like epsilon over 2 B prime is contained in B plus epsilon over 2 B prime, right? I take the volume of both sides. This is less than the volume of this. Now these are disjoint, right? So the volume would be just the sum. There's no inequality here, so this would be equal to J. Let's say this is J. J from 1 to m. And then the volume of each one is just going to be epsilon over 2 to the D volume B prime, right? And then this side is just going to be volume. I'm going to take an epsilon over 2 factor it out. So 2 over epsilon plus, so B plus B prime. And this side would be like epsilon over 2 comes out to the D, and I get volume 2 over epsilon B plus B prime. Right? I can cancel these two out. So what I would get is M volume B prime is less than volume 2 over epsilon B prime. Okay. So that's there. So did we use maximality actually? Where did we use maximality? So that proves it, because if I divide, I get this span. So is there any place where we use the fact that this is a maximal? Sorry? Who said something? Which inequality?
Like the upper bound on the fractal fraction inside any size epsilon fraction less than that.
Right. Right, but it seems like we did not require that. So you pick any packing, any epsilon packing. I mentioned this, but this is only used in this part, right? If I just want to like prove this inequality, it seems like the argument that we did works for any packing. And so we showed that any epsilon packing satisfies this. So by definition, the maximal one has to satisfy this as well. So the argument doesn't require, this part of the argument doesn't require. So not needed, it seems. Let me know if for, let's say, inequality B, which is this guy, call this B. You need it for this, but not for that. Okay, so the argument is simple, just compare the volumes. The difficulty is like computing these volumes. So let's say if one of them is L2, the other one is L1, you have to just compute the ratios of the volumes. And you can see that depending on the relative sizes, you could get different numbers. The easiest case is where the two walls are the same. Questions? Sounds good? Okay, so I just want to like very briefly talk about two non-parametric classes, whether we're going to use them or not, we'll see. This one, I encourage you to read. So if you have a parametric class of functions, something like this, 1 minus e to the negative e theta x, where theta is in 0 to 1, you can like easily reduce it to controlling the basically packing of the unit interval in the like it's in norm. So the packing number of the set is just going to be like of the order of 1 over epsilon, as you'd imagine. So parametric classes, oftentimes you reduce it to something like this problem. Do it as an exercise for yourself. What I would like to do here is talk about this Lipschitz class. And I just want to be brief. So if you look at the class of all functions from 0 to 1 to R, where f is Lipschitz with Lipschitz constant L. So that's the definition, if you recall. This class has entropy number. So entropy is the log, right? Entropy number in the infinity norm. Infinity norm is the sup norm. So this is like n delta FL, and then the sup norm. Sup norm of a function is just supremum, let's say x in 0 to 1 fx, right? So uniform norm or sup norm or uniform norm. Uniform. So the log of it is like L over delta. So if you compare with let's say log n delta ball L2 ball in the L2 norm, that would be, I'm going to have to take the log here. if I take the log, the metric entropy would be d log 1 over epsilon, or d like 2 over epsilon. So this would be of the order roughly would be d log 1 over delta. Okay. So the metric entropy of a finite dimensional ball, d-dimensional ball, is d log 1 over delta. This is L over delta. So you can see this grows like logarithmically 1 over delta. This grows polynomially. So this is much, much bigger. If you do it in covering numbers, it would be like e to the this. So this is polynomial. Covering number is polynomial in 1 over delta. The covering number here is exponential. Or the log entropy is, the log covering number is polynomial in here. This is logarithmic here. Okay. FL is much more massive. So you can measure how big it is by how fast the covering number grows. And I'm just going to hint at the proof. So there are some homework problems in high dimensional probability book that proves the upper bound. The interesting thing is the lower bound. So you can show that this has to be at least this much. Okay, so you can't improve this. In order to prove this, what the idea is, you embed the cube, the -1 and 1 to the m, inside the space for sufficiently large m. This is a combinatorial set. There are 2 to the m objects in there. So you can see, like, if I take m to be like roughly 1 over delta, if I can like embed this cube for m 1 over delta inside that set, then the covering number has to be at least this much. So in order to prove this, you would show a packing. If I want to do a lower bound, what I can do is I can show a lower bound on the packing number, basically, if I'm not wrong. So if I can, maybe let me just mention this. So if I how do we show this? Do we want to show this? Or do we want to not show it? So the idea is you have, so if you define this phi, just maybe mention it, it's interesting. So 0 to 1, that's phi, right? And then I'm gonna, so continuous extension to R. So we do continuous extension. I believe. Maybe I want to do this. Just verify for yourself, like function like this. Okay. That's phi. Not continuous, but there are many ways to do continuous extension. But then if I form these functions, so I'm basically, so this is rescaled and shifted to, so you can see so L epsilon phi y minus xi over epsilon. This will have, this is Lipschitz 1. This would be like so that xi starts to go up, and then xi plus epsilon, so reaches the maximum, and it would be L epsilon, something like this, right? And you can see because I move epsilon apart, and then I get like the slope is like L, so this is L Lipschitz, and then if I combine these, each one is like this in a particular interval. If I make these epsilon i's epsilon apart, these things would be disjoint when I sum them over like m of them. I get, for example, one here. The next one, there's a sign here. Okay, so the next one would be like something like this, perhaps. Like looks like that. The next one might be like the other one would like again be like this. So when I add them up, it just either go up, down like this, or just keep going up. So you get these things, right? So depending on like the sign of these coefficients that I have here. So beta I, like beta is a binary vector in m-dimensional binary vector. Each coordinate is -1 and +1. So this construction, if you look at it, it produces these kind of paths. So you get a function. So if all of the betas are 1, just straight goes up that like straight, and then if the first two are 1, and then -1, -1, 1, and so on. So if you take a look at this, and you can see that the slope here is always at most L, right? So it's a Lipschitz. Each one is a Lipschitz function, and so that's this part. And then you can see that the soup norm, in terms of soup norm, if you pick any two of them, there's at least one interval in which they differ. There's at least one element, and then over that, they have to like be at least 2 L epsilon apart. So they have to be this much apart, right? In the soup norm, they're going to be 2L epsilon packing. And then, so yeah, so that's sort of, if you pick any two different betas, the two functions in the soup norm, so that the maximum difference is 2L epsilon. And now if I take the epsilon to be delta over L, so this would be a 2 delta over L. The L goes away. So this would be a 2 delta packing. And M would be, I wanted these to be disjoint. So M would be basically 1 over epsilon. So I'm subdividing 0 to 1 into intervals of length 1 over epsilon, right? So yeah, so M is like roughly 1 over epsilon. So 2 to the M would be 2 to the delta over L. So I have this many functions. So this is saying the packing number of this class at level 2 delta in the soup norm is at least 2 to the delta over L. Where right, sorry. Right. This is bad. So this would be 2L over delta, I think. Yeah, we wanted to blow up. So L over delta. So you get L over delta. So that shows the lower bound. So the packing number grows exponentially in 1 over delta. So it's like e to the, so we showed it like m infinity 2 delta. If L is bigger than this, okay? And then this is a upper bound, like a lower bound on, so this is a lower bound on the covering number, okay? So that you would hopefully show for yourself. So you have something like this. And then for the upper bound, you can try to use a similar argument. But the thing is, this is the interesting thing. So this is, you need this much. You can't do better than this. And it's exponential in 1 over delta. Okay, so it's really a massive set. You can see basically, and these are not crazy functions, right? So they're sort of benign functions. It's just that if you want to just assume that your function looks like this, but you don't want to assume anything else about it, if you want to search over this whole space, then you have to be able to differentiate like this guy from the one that just goes like one goes up down and then the rest is the same. So if I want to just, let's say, distinguish between this and the one that just goes down in one place and then follows, right? I have to pay this price. There are this many sort of possible distinct functions here. Sounds good? So this construction you can extend to the d-dimensional space, and so you get L over delta to the d. This is again the log metric entropy. This is really, really bad. There's like a curse of dimensionality. So it's like something like n infinity of delta. This is like e to the L over delta to the d. Okay. So it's like super exponential in d. So that's really the curse of dimensionality. So like estimating a like Lipschitz function in d-dimensional space is really hard. It's like hopeless. And so this translates easily to rates. So the rate at which your estimator goes down gets very slow as d grows. We may hopefully talk, I'm not sure, but we can talk about this at some point if we get a time. Like you can translate easily these to rates of convergence. How do you mitigate this? You could mitigate it by imposing more smoothness assumptions. Okay, so suppose, for example, the derivatives are bounded. So the Lipschitz class, so this is equivalent. So FL is the same as the set of all functions that are f prime exist almost everywhere, respect to the Lebesgue measure, and f prime. I'm going to do the soup norm. The maximum is at most 1. Okay, so the derivative is at most 1. This is saying f prime x is less than or equal to 1 for all x in 0 to 1 at which this exists. Okay. So Lipschitz condition is a boundedness of the first derivative. So you can require boundedness of higher order derivatives. So you can say like j from 0 to alpha, all of them are bounded, and then the last one, let's say the alpha one, is also like this Holder continuous. It's like halfway. Gamma could be like between 0 and 1. If it's 1, it says that it's just Lipschitz. The final derivative is Lipschitz, which means that the next derivative is almost everywhere exists and bounded. But it could be like Holder continuous, it would be halfway there. So it's like between continuity and Lipschitzness. And then you can show there's a similar argument in the book. I just have to change the construction. You change these basic functions here to more smooth functions. So these are not smooth, so that the second derivative doesn't exist. But if you smooth it out, so there are functions that are things like this that are smoother, and then you can show that at least the lower bound, you can show the upper bound, hopefully you can show that it's like the metric entropy, like is the 1 over delta to the 1 plus alpha plus gamma. So 1 over alpha plus gamma, right? So it just reduces. So when alpha and gamma are big, let's say gamma is 1. Let's say gamma is 0. So gamma is 0. It's just the alpha derivative is also bounded. So it's like 1 over alpha, okay, or 1 over alpha plus gamma. And then in the d-dimensional case, it would be like 1 over delta to the d over alpha plus gamma. So let's say gamma is 0. For simplicity, so you get 1 over delta d over alpha. So it just contracts this d. So if you have more smoothness, you can just effectively counteract the dimension and recover the rate. So that's how you could do like non-parametric regression. If you're willing to assume more smoothness, you can sort of mitigate the carousel dimensionality. Questions, comments? So if we get to talk about non-parametric regression, you will see how these can be used to drive the rates. But for now, so the real interesting sort of aspect is like doing these for function classes. So like what are the entropy numbers of different function classes? But it's just good to remember that there is this example of a Lipschitz class or these smooth function classes for which the metric entropy is on a different order. It's like compared to the finite dimensional setting. Okay, questions? Okay, so let's move on. So that's like a detour. Now I want to use these to prove some results. I'm going to use the finite dimensional, the one about balls that we talked about, and to study random matrices. So the first thing that we're going to do is, so if you recall, we studied random vectors whose entries were sub-Gaussian, independent sub-Gaussian, and so we start with that for matrices. So consider a matrix whose entries are independent sub-Gaussian, and so if you recall, there's a psi2 norm. So I'm going to assume that the entries of A have psi2 norm at most O of 1. So there's just, it doesn't depend on M and N. So that, for example, Bernoulli, like Rademacher, or Gaussian, or any bounded variable. Then the result I want to show is that the operator norm of such a matrix roughly scales like root m plus root n. And so a formal result is this. Suppose A is an m by n matrix. The entries are independent, zero mean sub-Gaussian. The sub-Gaussian norm of the entries at most k. Then with probability 1 minus e to the negative t squared, we have this result. So we have this t here, which allows you to improve this bound, the probability bound. But the basic idea is that this is roughly of the order k is this bound on the sub-Gaussian norm, but root m plus root n. And this uses metric entropy ideas, discretization argument, basically. But before doing that, let me mention that this is why this is interesting. So it's good to have some sort of a sense of whether root m plus root n is a good bound, or it's just something that you would have expected, or it's always good to sort of check in some simple cases. So this bound is quite impressive, because if you have, it's because of what I wrote here. So if you have, suppose I have aij in negative k and k. So if they're randomly distributed in negative k and k, right? And then they're zero mean, then they're going to be sub-Gaussian with bound, like sub-Gaussian norm will be bounded up to constant by k. So this result would hold. But if they're deterministic, so deterministic here, and then I form the operator norm of A, this could be at worst, say the worst case is like root m times n, rather than root m plus root n. The easiest way to see is like just do k 1m 1n transpose. So this is a vector of all ones of size m, a vector of all ones of size n. So this is basically just a matrix whose elements are just all k, right? A deterministic matrix. All the elements are k. So how do we compute the operator norm of this? the sum of all the elements, the sum of all the elements is not a norm. If you square them, take the sum and then the square, that would be the Frobenius norm, right? And in fact, it's actually going to be in this case equal to the operator norm, but why would that be the case? You could do like in this case, it turns out that this is equal to the Frobenius norm in this case. But can you argue one way or the other what this operator norm has to be? Yeah.
Square matrix. Write it as an outer product of one vector itself.
Yes.
And then the general transpose itself.
So it would be like, let's say 1n transpose. Yeah, so forget about the k for now. Just k is going to rescale everything. So
That's a projection of the space of.
you're talking about this projection? Yeah, it's not exactly the projections. If you do something to it, it would be a projection matrix. Yes, so if I rescale it, this would be a projection matrix onto the span of 1n. Okay, so what is the conclusion?
That's all the other numbers are 0.
Right. So, yeah. So you can also see it here. So this is a rank 1 matrix. Whenever you have like n by 1, 1 by something, the inner dimension would determine the rank. So this is rank 1. So there's just going to be one non-zero eigenvalue, right? And then you can determine it by guessing. So let's say we guess that if I multiply this by 1n, this would give me n times 1n, right? So this has to be an eigenvector, and n is the eigenvalue. The same goes here. So this is going to be like singular values. So if I multiply this by 1n, I get k 1n n times n, right? And right, then you have to normalize things. It's a little more tricky for the singular values, but it's a rank 1 matrix, right? And for rank 1 matrix, there's one non-zero singular value. It's like non-zero. One in this case, you can see it's n, so it's going to be like root. Yeah, so like n and n are the same root n squared, which would be n. So that's the case. In this case, because it's rank 1, so the sum of the singular value, this is like max sigma I a. This is going to be equal to the Frobenius norm. It's easiest to do this way, right? Just whatever. So our rank is actually 1. So this is going to be equal to Frobenius norm, which is going to be equal to like k times like the m n, and then you have to take the square root, right? It's easiest to see it that way. In any case, this is of the order root mn. You can also do it by singular value. Compute this. This should be the singular value, the largest singular value, which is non-zero, basically. Comparing with this is much smaller. It says that if you randomly pick these and then there's zero mean, the operator is much smaller than the worst case that it can be. So next time we're going to come back and try to use the metric entropy ideas to prove this. And then you can use this to like prove other things about random matrices. Okay, thank you. See you next time.